Welcome, everybody. This is our first Quantum Materials and Devices seminar of the semester. I am pleased to welcome Roman Gorbachev from University of Manchester to speak on optoelectronic properties of 2D semiconductors. Thank you very much.
Thank you very much for inviting me. So I work at National Graphite Institute, which is part of Department of Physics and Astronomy. I lead a nanofabrication group, which deals mostly with 2D materials. The activity of the group can be basically described in three large directions. So the first direction is optoelectronic properties of 2D materials, primarily TMDs, and also a lot of work on indium selenide. That is what I'm going to talk today about. The second direction is to do with TEM microscopy and using 2D materials to create small isolated pockets of liquid or some chemical solutions, and then observing reactions in situ in a TEM at atomic level. And the third direction is to do with advancing 2D nanofabrication technology and trying to create heterostructures, layered heterostructures of 2D material in ultra-high vacuum. So out of three directions, I think most suitable for this community would be the first one, and that is what I'm focused about on today, but you're very welcome to ask me questions about the other two later. Now, probably most of you have heard about Twisttronics, and it is now a very hype and very large direction into 2D materials. First explorations or first ideas about Twisttronics began back in 2007 or 8. Although the technology was not at a level back then to allow proper device fabrication of the control of the twist angle. Starting from about 2013, there was a large boost to this field when people started looking at graphene on top of boron nitride, which, when they aligned, create so-called Moore pattern. So the lattice constant of graphene is 1.8% different from boron nitride, and it's also hexagonal. So when you put them on top of each other, you can see there is the superlattice appearing, and if you then start rotating them relative to each other, you can control the period of the superlattice. And that is what Twisttronics about. Despite the weak nature of van der Waals forces between graphene and boron nitride, the superlattice introduces very major changes in optoelectronic properties of 2D materials. And for graphene and boron nitride, for example, it led to so-called Hofstadter butterfly, where you have additional Dirac points forming in the spectrum of graphene, and it changes into a physical fractal in magnetic field. Then sometime later in 2014, there was a discovery of so-called lattice reconstructions in the same system, which we will be talking today quite a lot about. And then the field sort of coasted for a while, and around 2018, MIT group published two large papers in Nature declaring superconductivity and correlated insulating states in twisted bilayer graphene at a specific twist angle, which is called magic angle. And from that point, there was a huge influx of research groups and activity in the field. And so a few years back, people started looking carefully into the TMDs. Now, transition metal dichalcogenides, a broad group of 2D materials, which mostly people focus on MOS2, tungsten sulfide and tungsten selenide. These materials have very exciting electronic properties and also very good optical properties, which in combination with Twisttronics makes this very interesting direction. So these papers here is just for you to sort of have some idea for later reading. Now, I mentioned lattice reconstruction, and I've chosen a paper here from Philip Kim, whom you probably know quite well. This paper was published in 2019, and it describes this lattice reconstruction process in twisted bilayer graphene. What you see here is a TEM image of these twisted lattices at 0.1 degree, and you see these triangular domains forming, which are basically commensurate regions or AB stacked regions. And it happens because the energy gain from the AB stacking outweighs the cost of these boundaries between the domains. So the lattices basically locally twist into perfect alignment. And then the strain originating from that goes into these so-called domain walls between them. And that is, of course, the period is controlled with the twist angle. So the larger the twist angle, the smaller the period. You can see this picture clearly illustrates that. And so we started looking into this, about 2.5 years back in TEM as well. And this is low magnification TEM. And the sample is suspended TMD bilayer, twisted bilayer. And you can see that because TMDs lack inversion symmetry, there are two possible configurations here, which are not identical. So when you align the unit cells parallel to each other, you have so-called parallel configuration, which in bulk corresponds to 3R stacking, 3R polytype of TMDs. And if you sort of put them opposite each other, you have the anti-parallel configuration, which is equivalent to 2H stacking in the bulk. Now, so of course we started looking closer into this, and when you look at large angles, say 2 or 3 degrees, you see that the modulation, this atomic resolution TM image filtered, of course, and you can see that there is a modulation of the atomic registry, but that is periodic and there is no domains. Now, if you take a smaller angle, for example, 1.2, 1.3 degree, you can see the formation of these triangular domains within which you can see a clear hexagonal lattice. So this is the commensurately stacked region. Now I would like to look in detail into these two configurations. So for the parallel configuration, we have triangular domains forming. That is very similar to graphene, twisted bilayer graphene. And if we zoom in into these little regions here, you can see that there is, as I said, there's the commensurate stacking region. We called it MX prime, which is basically for metal in one layer aligned to the chalcogen in another layer. And the next triangle would be a mirror image of that. So that would be chalcogen in one layer aligned to metal in another one. In between, you have this transition region where there is no stacking. So the stacking changes, evolves continuously. There is no domain formation. And this region also concentrates a lot of strain from that reconstruction. And lastly, there is this little region here, which we called XX, where chalcogen is on top of chalcogen. Now, if we look at the energetics of this stacking, so this is DFT calculated adhesion energy of these configurations, you can see that as a function of interlayer distance, the MX and XM stacking types are the most favorable. They have lowest energy. So this minima would be where the layers prefer to sit. They also sit closely to each other. That means within these domains, the layers would be closely packed and they would influence each other much stronger. Now, if you look at, for example, XX configuration, it has much higher energy and it also has a higher interlayer distance. So if you look at the distance of interlayer, so map of interlayer distance, you can see that it's small within the domain, it's large at the boundary, and it's very high at this high symmetry XX point.
Roman, if
Yes.
I can interrupt for a second. I'm sorry I didn't introduce you. My computer crashed and I should have, it's crashed exactly when you joined. So I apologize for this. I don't want to stop you in the flow. I just wanted to add that usually people ask your question and they put it in the chat, and then in the end,
Sure.
we can address it. So if people have questions, please put it in the chat, and Roman can look at it at the end or during. I will collect it as we go. Okay, so I just wanted to apologize, but I don't want to stop you now. I think
that's okay, no problem. Yeah,
okay, fine. Thank you.
So going back to the second configuration, which we call antiparallel. Yes, antiparallel here. We would have, so there's a strange, yeah, there you go. So in antiparallel, the picture is very different. So we have this, we also have domains, of course. One of them would be 2H stacking, which we normally would see in exfoliated bilayers of TMDs. But there is a second region, which is we call MM, metal on metal configuration, and it has slightly higher energy, but not much higher. So you can see both domains forming. However, the 2H would dominate. It would impinge onto the MM domain, sort of squeezing it from the sides because it's more energetically favorable for the material to be in 2H configuration. The same idea here. You can see that the interlay distance varies. It's highest in these high XX high symmetry points, and it's lowest where they are stacked in 2H configuration. Now, after looking at the properties, of course, we have to have a look at the other things. Sorry, yes, there you go. Apologies, the presentation seemed to have reshuffled slides. This is a topography map in AFM, in contact mode. You can barely see the boundaries between these domains, and that corresponds to the slight 50 picometer variation of the interlay distance between the layers. It's much easier to see this in friction, though the contrast is quite low. Now, if we take a conductive tip, you can immediately see there is a contrast popping up. And that really puzzled us for a while, and we started looking into conductive AFM. So in conductive AFM, very quickly, we realized there is something interesting going on, because you can see this huge contrast between the domains. So what we're measuring here is the current between the tip and the sample. This twisted bilayer is sitting on a bulk graphite flake to provide a drain for the current. And as we scan, we can see the variation of the current at a constant sample to tip distance. And regardless of the bias applied, this ratio seems to be around 1.7. So the current ratio between dark domains and bright domains is about 1.7. So that puzzled us, and it's sort of hard to explain, because if you look at, for example, DFT, and both DFT and RPIS show that the band structure for these 3R2H configurations are very similar. So there should be really no difference between the tunneling current if you just considering the band structure of the material. Plus, these domains are mirror image of each other, so they should be really identical. And now what's happening here is the lack of inversion symmetry, and that allows the wave functions for the electrons and holes to be layer polarized. That means that if you look at a specific state in the band structure, for example, here at the bottom of the conduction band, the wave function would have more presence on the top layer, for instance, for MX configuration, and it would be inverse for the XM configurations, the higher wave function presence on the bottom layer. And this is what we're basically measuring. When the tip is present on the bright domain, we have a higher density of high wave function presence on the top layer, and it's easier to tunnel into it, hence the higher current. When we go to the next domain, it's basically looking face down and exposing low density of states for tunneling. The same would, of course, happen for other TMDs. This is a very generic feature, though the ratio would vary depending on material. So, for example, here we're looking at tungsten sulfide, and you can see the ratio is about 1.4. Now, having studied this interesting wave function asymmetry, we started sort of trying to study evolution with the twist angle. So what happens when these domains are tiny? What happens when these domains are large? And no matter what twist angle was for 3R or for the parallel configuration, the domains were always triangular and always identical in size. And that is because, of course, the energy are equal, so they would always occupy approximately equal area. Now, for the antiparallel configuration, because the 2H polytype was dominating energetically, as the twist angle decreases, you can see that it takes over the sample. So here it's already at 1.6 degree, it's already encroaching onto the domain. And if you make the twist angle even smaller, it occupies huge area, and the domain basically remains as a seed of this second state metastable phase. It would always remain around, say, at 5 to 10 nanometers in size. So eventually, when you have a nearly zero twist angle, the sample would be primarily 2H stacking with tiny seeds of these domains for every odd vertex. So it's like a hexagonal domains now with tiny triangles at the top. So if we look at conductive AFM of this anti-parallel configuration, we don't see this alternating bright and dark domains. In fact, it's very hard to see this, what we are showing here. So that is, again, a variation of current as we scan across the sample in contact mode with conductive tip. But even that is hard to explain because basically what we're looking at is two polytypes with a very similar band structure. The band gap is very, very slightly different. And there is no asymmetry here because these are centrosymmetric systems. They should both have symmetric wave functions of both layers. So this was hard to explain until we started looking into the strain. So of course, the reconstruction that we're seeing comes with the strain distribution across the entire system. And then we worked with Volodya Falco, who is a theoretician in NGI, to develop a model. So this is basically an interpolation phenomenological formula that approximates the adhesion energy and gives a precise position of atoms in the reconstructed lattice. So here you can see it's overlaid on top of TEM. So black and white is TM image. And on top, you can see red and blue positions of predicted positions of the metal atoms. So that allows basically to extract displacement of each atom from its initial position as in non-reconstructed lattice, and looked at the strain map and resulting piezoelectricity map. So these materials would possess piezoelectricity, monolayers do, bilayers don't. And the reason for that is in bilayers, you would create piezoelectric charge, which is opposite in top and bottom layer normally. Now, in the lattice reconstruction, the situation is different because when they click in together, they have opposite displacement. So one layer moves left, another layer moves right to sort of meet in the middle into commensurate stacking. And because of that, the piezoelectric charge is actually the same sign on both layers. So it creates this texture, piezoelectric texture, that is accompanying with a lattice reconstruction, which has high density in these points, and so high positive density and high negative density in XX points. So that piezoelectric charge would be screened by free electrons or thermally excited electrons, and it would basically at room temperature create little pools of electrons where we don't quite see quantization because you need cryo temperatures for that. But you can still see a high density of electrons locally near these points because they've been screened by the free electrons. So just to kind of summarize what we've been talking so far, so there are two configurations, parallel and anti-parallel. They result in a very different layout of the reconstruction, with parallel being triangular and equal, anti-parallel being mostly 2H with small seeds of stacking. And the reconstruction creates piezoelectric charge distribution that would modulate the electronic properties. Of course, the situation is more complex than that because also you modulate the band gap H. So if you sort of scan across this more pattern, you would see that the electrons would have minimum in K valley near the region, while holes would have the minimum for energy in gamma near the XX point. So that can create all kind of interesting optical and electronic phenomena. In fact, there were papers showing that there is quantization in the system. And so both electrons and excitons become trapped locally by this Mora potential. Now, in the parallel configurations, the piezoelectric charge has opposite sign in 2 layers. So there is no charge overall. However, the charge is opposite on top and bottom, and there is a polarization across the bilayer. And so that is also quite interesting. We'll talk about that later. So this lack of symmetry actually produces both charge transfer and piezoelectric charge dipole across. So here we come to the point of ferroelectricity, which is fairly recently have been discussed in hexagonal boron nitride, twisted interfaces, and also in tungsten telluride. The ferroelectricity occurs because, yes, you can create this asymmetric interface between 2 materials, and that can lead to the charge transfer across the interface, and of course create polarization, which is in practical terms, ferroelectricity. This is different ferroelectricity because we normally use to some sort of change in the lattice clicking structure. Some atom moves in between 2 metastable positions, while here this is created by the electronic cloud, which is basically has 2 preferred configurations and can move from one side to another. So switching of the domains is performed by sliding these materials. So if you want to switch from MX to XM, you can slide crystal slightly along the plane, and that would click into the other configuration with opposite dipole, electrical dipole. So we started looking in TMDs, and the reason, of course, it would be very exciting to have a semiconductor, especially with very good optical and electronic properties, which also has ferroelectricity, because that can be employed for different memory functions and some kind of novel functionality that we can employ. And so if looking at these domains, again, this is a map of typical sample. The tool we selected to visualize this map is called electron channeling contrast imaging, which is basically you shoot the electron beam at an angle in SEM, and when it's aligned with the lattice columns, atomic columns, you have change in the scattering, and that signal would be different for different domains because they have different stacking order. So you can basically highlight the domains using this technique. This has been employed. There is a reference here if you want to look further for secondary electron imaging. Although here we prefer to use backscattered electrons for a better contrast and better resolution. The schematic here shows the domain, so MX or molybdenum sulfur domain on the left, and a sulfur molybdenum domain on the right. And in the middle, we have this partial dislocation, which we also call the domain boundary. But in crystallography terms, it is partial dislocation. And when we look, so here's the illustration. It's very sort of basic illustration, but it helps to understand the process. When you shoot a beam at this angle, you have more electrons coming out because they basically scatter more on this specific polytype at that angle than this configuration. And the next thing we would do is we encapsulate this twisted bilayer with boron nitride and 2 graphene layers from each side. So graphene layers create a back and top gate, and they allow to create transverse electric field across the TMD bilayer. Now the bilayer has built-in electric field as in ferroelectric field, and what we're trying to do here, we're going to switch this domain by applying external electric field to it. Now, in order to switch, as I said, you need to slide one crystal. So the way of switching between one configuration and another configuration is by sliding this partial dislocation towards one of the domains. So whichever becomes more energetically favorable in external field would start expanding. And you can see it here. So we selected this area with large sort of domains which have random structure. And we started applying the transverse field. And you can see that so we start actually with high transverse field. Then when we withdraw into 0, the domains don't really change. But then when we inverse the field, you can see that the domains start collapsing, the dark domains start collapsing, and it basically squeezed into this narrow line, which is barely visible. And another one here. Now, if we go back to 0, nothing changes. So that is, basically the hysteresis loop, if you like. And then if we apply positive field again, it restores the configuration that we saw in the beginning. It is also important to notice that there are some contaminations, and they've been sort of picked. The region was picked on purpose. You have these little bubbles of contamination, and they would pin the domain structure. They would not allow the domain wall to slide past them. So these do act as a pinning center, and that also means if you want your device to switch nicely, you actually need to have very little contamination in the samples. So here's a little bit more on this. So these are sort of raw images, slightly enhanced contrast. You can see the domain switching. And what I wanted to illustrate here is that when you go from 0 to high field, the switch doesn't happen instantaneously. It happens over progressively as you increase the field over the entire range. And the reason for that is, of course, some sort of local pinning, small defects and things like that. So far we discussed large domains, so it would be interesting to see what happens in these little triangular domains. And so we looked into that. And also this is the same structure. So there are 2 gates. We're applying the field across. We start with this nice triangular configuration at 0 electric field cross. And then when we apply positive field, you can see that the black domains expand and the bright domains contract. And when we reverse the field, opposite happens. So dark contract and bright expand. So the overlay on top is actually a model that you can find in this paper. There's a paper now on CondMat that you can find about it. So again, our theoretical group led by Volodya Falco developed a nice model that can basically predict the shape of this network at a certain electric field. Another thing that happens here is if you pick large domain size, you can see that they actually, these 2 opposite domain walls, as you increase electric field, they would touch each other. So they form this new kind of defect. But if you look at this very carefully, it's not a new defect, it's been known for a while. So you basically merge 2 partial dislocations to create a perfect dislocation in the middle. Now, because Berger's vectors for these dislocations are pointing along the opposite, so they're not opposite, they would not be able to basically remove each other from the system, and you would always have this perfect dislocation left. And that would be when you reverse polarity, that would be expanding, and opposite will happen. So now you can see that these two merge together here. It's very hard to see because obviously contamination builds up as you measure. So the contrast degrades, but barely see here dark domain, which is the collapsed domain. Now there is a model that describes that, and basically what it says is that there is a universal scaling in the system. If you take the length of this triangular domain, multiply by the electric field, by the displacement field, you would allow some sort of universal scaling. So if you look at this, for example, picture H here, you can realize this layout either by high electric field and small domains, or you can use small electric field and large domains, and they would create the same shape of the layout. Right. So now, having measured so far structural properties, we were looking at the electronic properties, of course. And so how would you look at this system to understand this built-in, to characterize this built-in electric field? And the tool we chose for this is KPFM, which is Kelvin probe force microscopy, which basically measures surface potential on the sample and allows you to map the surface potential. Now, for that, sample needs to be grounded, so we connected graphene contact overlay and graphene contact, and then we deposited the shadow mask contact, so everything is nice and clean. There is no resistor here. And after that, the idea here is that, okay, you have these two domains next to each other. One of them has the displacement, so the polarization up, the other one down. And as you measure the potential with the tip on top, this built-in field would either add or subtract a certain delta V from the equipotential plane of the backgate. And what we're measuring, in fact, is exactly that. So this is KPFM surface potential map. And you can see that the domain structure is clearly visible. Now here, there is the way to sort of quantify that is as you cross from one domain to each other, you measure two delta V's, because on one of them is plus delta V, another one is minus delta V. So the jump in the potential is basically 2 delta V, which we measured to be about 110 milli-electron volt. It depends on the sample, but I would say 105, anywhere between 100 and 110. The measurements have been done in ultra-high vacuum for KPFM to prevent any kind of surface contamination of water, changing this value. So this, we believe, is pretty accurate. And in fact, it actually does agree with theory quite well, which predicted, I think, 116 milli-electron volt potential. Now, interesting thing happens if you start doping this system. So we had a sample which had a backgate on which we could perform KPFM measurements at the same time. And as you apply positive backgate, you introduce electrons, free electrons into the system. You can see that those free electrons now can move in the crystal and screen this built-in electric field. So as you apply a very high gate, you can see that the domain structure sort of disappears. Of course, it doesn't structurally, the structure is still there. What disappears is the electric field or surface potential that we measure due to the screening. However, this corresponds to about 10 to the 13 electron density, which is pretty high for this kind of system. And anywhere in between, the screening is only partial. This partial screening tells us that even though there are free electrons in the system, the fact that the wave functions are layer polarized do not allow them to actually freely move between the layers and screen it entirely. So you need a very high density of electrons to actually screen it out completely. So here's a sample on graphite. The previous sample was gated on boron nitride. This one is on graphite. We see very similar thing, the same value of potential, about 100 millivolt here between the domains. what is interesting here is that, yeah, we can switch it with a double gated structure, but can we switch it or control it with the tip? And the answer to that is yes, but it's not very controllable. So here is the EFM map, as I recall, or KPFM map. And then what we do, we go and scan this little region in the box in contact mode while applying a voltage to the tip. And you can see that after the scan, this domain structure inside is completely reshuffled. So it is definitely changing. But there are two things happening here. So firstly, you're scanning in contact mode, meaning that you can actually apply mechanical force and move the domain walls with that. And the second is, of course, you're applying electric field, so that is influencing the sample. And though you can see that some of these nodes are now pushed out of the sample, the intersection of the domains actually has been pushed out of the sample. The switching is not reproducible. Basically, every time you scan, you would end up with some new configuration, which is not very controllable. Now, can we switch with just the voltage? Yes, we can. So if we just hover over the sample at some 10, 20 nanometers above, we could switch.
Sorry, a question about the previous slide, just to understand the previous slide. So this is a conductive AFM images, right? And the gating is from below, right? That's
so these are so sorry, for this slide, yes, this section panel D and E are gated sample, and the gate is from underneath with a local graphite gate and the measurements of KPFM from the top.
I see. Okay. There was also a question, how did you calculate the doping level? If you can answer.
Oh, so that is from transport measurements, basically, and the thickness of boron nitride. The boron nitride here is the gate dielectric, so we know the thickness, and we use a flat capacitor model, and we take the conduction band threshold value from the transport measurements that we did.
Okay, thank you.
Okay, so back to this. So we can also switch these domains using just the voltage, but again, it's not very reproducible and not very controllable. Maybe over time people would learn to do it better, but at the moment you can see the change, but it's not directional. Now, of course, we try to do electronic transport measurements, and here the samples that we measure, again, double gated. They are in the whole bar geometry. The next thing we do, we apply a small back gate to introduce some electrons into the system, so the system becomes slightly conductive. And then we change the top gate, which at the same time changes carrier concentration and applies the transverse electric field. And so here you can see the sweep of this is conductivity as a function of the transverse field. As we apply the electric field across or the gate voltage, the top gate voltage, the return is on a different path, and there is this hysteresis in the conductivity, which changes both as a function of the maximum voltage you apply and the backgate voltage that you have at the moment. So this would happen for for monolayer system. That also happens for trilayer system, because the interface there is also 3R and it's also asymmetric. So it also has the ferroelectric domains. However, if you try to do 2 and 2 layers, twisted at 0 degrees globally, that would produce 2H domains, which are not ferroelectric. And there you don't see significant hysteresis. In fact, the one you see is actually opposite sign. So this is hysteresis, classical hysteresis due to some gate traps, and it actually has opposite sign here. So the same happens with just exfoliated crystals, which are 2, 3, 4 layers, no hysteresis. And lastly, we try to measure the 6 layers of 3R polytype. So you can actually acquire crystals which are bulk 3R polytype, and they're supposed to be ferroelectric, but they don't switch. And the reason for that is they don't actually have grain boundaries inside, because switching is done by moving these boundaries. You cannot switch them because they don't have any. Now, you can create an opposite domain in the middle of infinitely large domain, but the energy cost for that is immense. So you would need 1-2 order higher electric fields, which is beyond the breakdown threshold for these bilayers, for the gating dielectric. So you cannot switch the system. You need to create a twisted system where there are domain boundaries that can be moved. Right. So let's have a look how much time I have. So how much?
You have 10 or 15 minutes more.
Okay. Yeah. So at this, so a little bit more on the switching. So the switching is reproducible. If you measure conductivity many times, you can see that it actually is pretty consistent every time switches to about the same value. However, there are some interesting processes there. So there is an instant switching, meaning that there is a very quick sudden change in the domain structure, but then there is a trail, which is a long-term relaxation. So perhaps those impurities and little bubbles, they do pin the domain walls, which slowly over time relax into this new configuration. The switching is also helped by the temperature. So the higher the temperature, the better they actually switch, because phonons in the system, they promote the movement of the domain boundaries, domain walls, and they release the pinning. And so if you, some samples, for example, they wouldn't switch at 200 Kelvin, but if you heat them sufficiently above room temperature above, they actually display a very high hysteresis.
Roman, there was a question, why does the in-plane conductance changes when domain flip?
That's a good question. And the easy way, so there are two components here. We're trying to build a model for this now. At the moment, it's very basic understanding, trying to explain the experiment. So one way to look at it is the device is asymmetric. So you basically have this delta across the bilayer, which adds a little bit of electrons on one side. Now, if it's a top layer and you're gating from the top, that results in higher overall net concentration, which has higher conductivity. If it's the bottom layer and you're gating from the top, then the overall concentration is not as high, and hence that. So the second reason is, of course, the domain walls, and we don't really know what kind of scattering processes happen at the domain walls. Now, by rearranging the domains inside a sample, we may create more domain walls on the path of the electron from source to drain. And if they scatter, which they actually should scatter, that may significantly influence the conductivity. But at the moment, we haven't actually measured like an isolated domain wall. That would be next step in this saga.
Thank you.
Right, so from this, if I do have 10 minutes, I'd like to show some other results that we had, and they are to do with another material, 2D material, semiconducting material that we worked on. It's called indium selenide, monoselenide. There is a big difference between indium 2 selenium 3 and indium selenide. They both semiconductors, but this one have pretty high quality. So the mobility, just to give you some numbers, cryogenic temperatures is about 15,000, and there are now better crystals where mobility is getting higher. So it is an interesting material, new system to study. Optical properties also interesting. So as you would expect, the band gap increases with the number of, as the materials get thinner. So for monolayer, you can see the band gap, bilayer 3.6. So the band gap for bulk, I think, is about 1.1 EV, and it increases to about 2.7 for monolayer. We'll get to that too, in a minute. But what's interesting about this material is these Mexican hat-shaped valence band. So you can see here that it has this very low density, very high effective mass, high density of states, and then it flattens out at about 4 or 5 layers. And you can see that in ARPIS, so these are again our results in ARPIS, done with collaboration with ARPIS, with Diamond facility in the UK. And you can see that this is the valence band for 1 layer, and then it still has this little Mexican hat for 2, for 3, but at about 4, it properly flattens out. Unfortunately, we couldn't actually dope it with holes. We want better crystals to be able to do that, but we could dope it with electrons. And that is actually quite interesting because the effective mass is very high here, very low, sorry, here. So you have pretty high mobility for those electrons. In terms of optical properties, so you do get this exciton, of course, which would emit light. The difference with TMDs here is that the lowest energy transition is polarized out of plane. So if you're looking from the top in reflected light, you don't actually see much photoluminescence. But if you cut out the block of this heterostructure and put it on a side, which is this is a lamella cut out of the sample with FIB, you start seeing pretty high photoluminescence coming along the plane of the crystal. And that is because the dipole is polarized across the layer. And here you can see the polarization dependence, which is basically aligned here. Material also has strong second harmonic generation, lack of inversion symmetry. It can be used for to create light emitting diodes, which is here. It's just a brief reference to a paper. Again, we have boron nitride on either side, 2 gates for graphene, but this time the boron nitride is thin, so 3 or 4 layers, which allows for tunneling of the electrons and holes. And if you bias the graphene layers sufficiently, you can actually inject hole into the conduction band while inject electron into the conduction band and hole into the valence band at the same time. And they would recombine in the indium selenide and emit light. That light would be depending on the band gap of the material. So here you can see this kind of LED structure with different number of layers, which emits at different wavelength corresponding to the band gap of the material. That is actually in infrared, so the coloring is fake, but that illustrates the idea that the light is sufficiently different wavelength. In terms of transport properties, the material quality is high enough to be able to confine electrons. So we measured both quantum dot geometry, where we could see Coulomb diamonds. We also created a one-dimensional constriction and saw ballistic 1D quantization here. You can see the steps here throughout as a function of the backgate voltage. The different curves for the different backgate voltage, while the x-axis is for the split gate voltage. So these are sort of classical semiconductor physics, but nevertheless, the material is very nice to work with. It exfoliates easily in thin form down to monolayer. And then we did maybe 6 or 7 papers on this material over the last 5 years, starting with ARPIS. But in the remaining time, I'd like to show you a slightly different thing that was more recent. So here we combine TMDs with indium selenide. Now this interface, you can see that in blue, this is the band structure of tungsten diselenide. In orange, this is band structure of indium selenide, and they have an indirect band gap, which is at gamma point. Now, this is trying to address this problem when you grow these materials and you cannot control twist angle for some reason. The properties would be hugely dependent on the twist, but in this system, they're not, because everything happens at gamma point. And of course, in K-space, everything rotates around gamma points. So when you create a system like that, it's basically invariant to the rotation between the crystals. And so that is what has been measured here. You can see photoluminescence from indium selenide, which has this primary A exciton at around 1.9. I think this is 2 layers. You have 2 layers PL from tungsten diselenide with indirect and direct transition. And then the combination in the middle, this is the overlap region, has PL at a much lower energy, which is due to this layer. It's direct in K-space, but it's indirect in sort of in real space because it happens between the layers. And that can be tuned in a broad range using the thickness of materials, because you now have two materials to basically pick and control the emission. And we measured it down to about 1.2 eV, but if you pick the right TMD, you can actually go to that sort of sweet telecom 0.9, 0.8 eV range to achieve that emission. So here's just a sort of accompanying theory that shows you all kind of different combination between tungsten sulfide, molybdenum sulfide, so all TMDs combined with indium selenide to achieve the emission you like. So it's highly tunable system where you can achieve easily pretty much any wavelength between, say, 0.8 and 2 eV. Right, so at this I would like to thank you for your attention. So here's the team that have performed experiments in my lab. TMDs, work on TMDs is mostly Astrid and Nick. Alex provided technical support. Indium selenide is mostly Joanna and Matthew. Then, of course, being in NGI, we heavily collaborate with a lot of groups inside here. So for transport, we work with a group of Andrei Gaim. For theory, with group of Volodya Falco. For electron microscopy with Sarah Haig. And for the KPFM, we worked with NPL, who have this nice system that can do UHV measurements. Thank you.
Roman, thank you very much for an excellent talk. And again, I apologize in the beginning, I couldn't introduce you. I apologize for this. So I'll ask a few questions that people ask me during, but if people have more questions, please put it in the chat so we can ask. The first question is a bit more practical. When you show the ferroelectricity in the TMDs, how thick is the BN in the SCM? How thick is the BN can be to get these kind of images when you encapsulate?
So that's a good question. So yes, you need a very thin BN to observe this kind of images. We need less than 3 nanometers would be ideal. Now, if you have only few layers, you cannot gate because you start tunneling through, right? So a sweet spot somewhere between 2 and 3. We could still have some nice contrast at 5 nanometers, but above that, it's getting very hard to actually resolve the domains.
I see. And if you put a graphene, one layer of graphene on top of a thin BN, then it's still possible to see.
It is. It is better with backscattered electrons because they don't really care about metallic plane on top. Secondary electrons would be affected more by graphene. But these measurements have been done through graphene layer because we needed gating. So,
I see. Right. Okay. The second question, in the hysteresis. So basically, when you push the displacement field, then you show basically in one of the, I'm just trying to extrapolate the question. So when you apply the larger displacement field, you basically at the end, you get kind of a one single big domain, except these disorder points, the bubbles that you showed. Now, when you bring it back, the question is basically, why are the lines, the lines, which kind of disorder, pins these lines except the bubbles? Because it looks like the lines are coming back roughly to the same position.
Roughly, but not the same. Yes,
but not the same.
You can see you can see here there is quite a lot of roughness along the edge. This one is pretty uniform. I mean, TMDs are known to have fairly high concentration of atomic scale defects. Depending on the growth technique, the vapor transport usually have more defects. I think it's something of the order of 10 to the 12, if I'm not mistaken. So it is a high density defects. It's very likely that those defects would pin them somehow because they do create strain field around them, and that would interfere somehow with the dislocation that is trying to propagate across.
I see.
But
okay,
more macroscopic defects pin them properly, like these little bubbles, they pin
of
them
course.
100%. Yeah.
Yeah. Okay, another question Giovanni has now is how fast could this ferroelectric switching occur?
So we didn't do any very fast measurements. I would say that the majority of what we can say, because we typically measure DC or low frequency in transport. So what we saw that is on the scale of some seconds, there is a huge change in conductivity. And then over the scale of next perhaps 10 minutes, you would see a slow relaxation on top of that, which is smaller compared to the initial drop.
Okay, and maybe the last question, unless somebody asks another question in the chat, is there was basically, if I'm trying to understand the idea, is if you make a few contacts in the bulk, okay, and then you change the displacement field, is it possible by displacement field, to force contacts to be able, to look on a small number of vortices? You see the question? Basically, imagine that you have a few contacts just placed in the bulk, and then you apply displacement field. So the question whether between these two contacts you would get like lines of domains which are connecting.
So is it lateral now? So you're applying field laterally, not across.
Yes.
So I don't think the lateral field would interfere too much.
No. It's not what I meant. So if you look from above, you have a few contacts like in the bulk of the material, and then you apply a vertical displacement field.
Yes.
You push it, so you basically, in the end, you should get a single domain. But if you have contacts, which are basically like kind of a bubbles, do you expect some connection between these?
Absolutely, 100%. I think that the contacts would absolutely pin the domains because they just big large defect, if you like. I can tell you even more. If you have edged edges in your heterostructure, those edged edges often pin domains too, because when you chemically treat the sidewall of your heterostructure, it often ends up sort of cross-linking two layers together. So they lose this ability to slide easily across. And that would also lead to pinning of the domain walls. Yeah.
I see. Okay, maybe last question from Shiroy. Did you observe negative capacitance in the FET structure?
No, we didn't look for it. It's a good question. We didn't look for it because, well, mostly because what I'm showing you has been measured in transport maybe a month and a half ago. So, so there is still a lot of measurements ongoing right now, and we haven't tried capacitance yet.
Okay.
But I think there is on CONMAT there is a similar paper from MIT where they do a different kind of experiment. They put this twisted TMD into the gate stack, and they put graphene on top, and then they measure transport in graphene. And what they see is a jump in concentration when the TMD stack switches polarization, because it either adds to your back gate voltage or subtracts from your gate voltage, right? So they can see it via graphene, not directly.
Okay, I see that there are no further questions. So Roman, thank you again for the talk. And it was a short visit in Boston, but but thanks again.
Thank you so much.
I would love to do this in person. Unfortunately, this is the way now. So
yes,
yeah,
sounds good. So thank you, Roman.
Thank you.
Thank you.